We are going to talk about properties of sampling distributions today, and we will cover the idea of unbiasedness and minimum variance. So a simple type of statistic used to make inferences about a population parameter is a point estimator. So that's a rule or a formula that tells us how to use the sample data to calculate a single number for the population, some population parameter that we're interested in. For example, if we want, we can use the sample mean, which is x bar, as a point estimator of the population mean, which is mu. So we're using one to predict or estimate the other. And here's a diagram for you. The population is the huge set of things that you're interested in, the population, the target population or the population of interest. For the sea turtles, that would be all of the sea turtles, and the parameters would be the mu and the sigma and even the median sometimes. So you would have those three parameters that you would be considering for the population. There are others as well. But then consider a sample is a subset or a smaller group out of the entire population. So here's our sample, and then here's our entire population. The sample is a subset, it hopefully randomly selected, and we use x bar to represent the mean of the sample. This x bar is used as a point estimator for mu. So we're looking at all the x bars and saying this is going to tell us what mu should be. And then the same thing with our S, the standard deviation of our sample, can be used as a point estimator for the sigma or the standard deviation of our population. Formally, a point estimator of a population parameter is a rule or formula which tells us how to use the sample data to calculate a single number that can be used as an estimate of the population parameter. So really formalizing how you're going to take information from your sample and use it to estimate your population information. And thinking about the turtles again, if we know the mean length of our sample of sea turtles, we can use that to find the mean length of our population of sea turtles. And shell length is what I was talking about. So often we can find different point estimators to estimate the same parameter, and each will have a sampling distribution that provides information about that point estimator. And if we look at the sampling distribution, we can figure out how large the difference is between the estimate and the true value of the parameter, and that's called the error of estimation. Because we know if we take a sample of a small group of items from a larger population, that maybe our sample is exactly the same as the population, maybe it's slightly off, and so our estimator could be off from our actual values that we're trying to predict. So we want to have some kind of way to tell if our estimator is overestimating or underestimating a parameter as well. And so we're talking about error analysis. And I think I mentioned this before. We want to know how far off from the actual value we are. So how far are you from the actual value you want to estimate? And then are you over, that doesn't look like you, or under the actual value. Okay, and then the last thing is, remember, we often don't know what our population parameters are. So population parameters are often unknown. So the more ways we have to judge our estimates, the more accurate and more dependable our statistics become. And I'll say the more we can measure the dependability of our statistics. And if you're doing an ethical job at doing statistics with a large set of data for a company or for wherever you end up using your statistics for research or whatever, the more you can give an estimate of the reliability, the better decisions you can make based on those statistics. All right, now let's talk about the sampling distribution. So for a statistic, will, or a statistic will have a sampling distribution, and it has the mean of that sampling distribution is equal to the population parameter that the statistic is supposed to estimate. If that's true, if they actually match up, where if I take a whole bunch of samples and I find the distribution of all the sample means, and it's a bell-shaped curve or a normal distribution, and the center or the mean of that distribution, a sampling distribution, is exactly the mu from my population, then I have an unbiased predictor. So if I know my population parameter, the population mean, for example, and I see that my sampling distribution is centered right exactly over the center where my mu is, then I know that it's unbiased. So that's what we're talking about with unbiased, that the two are equal. And that means that your population mean is here, and your sampling distribution for X bar, the center of it is also in that exact same location. And so this would be unbiased. Now, if you have it slightly off, this would be your mu over here, and this would be your sampling distribution mean, which would be the middle of your X bars in our example. So we can use this idea, this would be biased because it doesn't match up. So our mean for our population and our distribution mean don't match up. So we're going to say that's a biased estimator because they aren't exactly the same. So if I use this mean for my X bars and I use that as my population mean, I'm off. And you can see how far I'm off. There's an amount of bias that we have there. So that one we want to say is a biased estimate of the parameter. And so we wouldn't want to use that if we had a better estimate. So here, this one is obviously the desired outcome, that we want our mean for our population to be exactly mirrored by the mean of our distribution of our sample means. For example, say that we are measuring the mean wait time for students that when they're waiting for their parents to pick them up from somewhere. So it's obviously going to be the ones who aren't driving yet. So if we're talking about the mean wait time, if we knew the population mean and it matched the mean from our experiments, so we did several experiments and we looked at the mean wait time for many students, and then we average those and we get this distribution of wait times for all the students, then that center of that distribution for the wait times, if it matches our actual wait time, the actual average wait time for all our students, then that would be an unbiased estimate. If, for example, we chose randomly, but we chose the 7 students or the 25 students who have a much longer wait time because their parents are forgetful, then we would have an unbiased estimator because it would probably have a distribution that was higher than our actual population mean. So that's the difference between biased and unbiased. And let's take a look at the standard deviation, because that's one other measure that we can use to determine how good our sampling distribution is. We can look at the standard deviation of a sampling distribution as another to measure another important property of statistics, and that's the spread of the estimates generated by repeated sampling. Okay, so suppose we're looking at 2 statistics, A and B, and they're both unbiased estimators of the population parameter. So both of them have the exact same mean for this sampling distribution. So statistic A is maybe the mean, and statistic B maybe the median of the same population, where we looked at our value here. Our mu is right here, dead center. And say the green one is our X bar distribution. So when we looked at a bunch of samples that we took from our population and we looked at the distribution of the X bars for those, we had the exact same center as, and this would be X bar here as well on the green one. So the green distribution is our X bar, and then the blue distribution maybe is our median. So we know we have 2 different measures of center, and say they both corresponded exactly with our mu. And so we know that both of those estimators are unbiased. And then the other thing we can do, it's a tiebreaker really, is we can look at the spread. So if we have more of our data clustered around the mean, the actual true mean, or in this case our X bar, which we've discovered was an unbiased estimator, then if more of our data is clustered, then that's a very small spread. And because it's a small spread, it's a better approximation for our actual mean because there's not as much variance, not as much spread going out. Now look at this one because that has a larger spread, and so that one's going to be larger spread. So in this case we would say not a very good estimator because while it's unbiased, it has the exact same mean as our population. It is spread farther out. So when you take any of the samples that helped create that distribution, you might end up with something way out here for your mean, which is not the same as our population mean. So it's way off from it. So this has less distance for you to have error. So this is basically the amount of error that you have. So this has less distance for your error, and the blue one has a lot more distance for your error. So if you had to choose between, in this scenario that I'm giving you, if you had to choose between the X bar and the median for this distribution, definitely choose the X bar because it has less error from the bottom. Okay, so that's what we're talking about. Since the means of the two sampling distributions are the same, we look at their standard deviations. So that's the tiebreaker, and it'll give you which estimates fall closer to the unknown population parameter that we're estimating. So we want to be as close as we can to that mu, for example. Naturally, we'll choose the sample statistic that has a smaller standard deviation. And here we have a picture of what we're talking about. Over a large number, and this is what you have to understand, over a large number of samples, the values of A cluster more closely around the unknown population parameter than do the values of B. So the probability that A is close to the parameter value is higher than the probability that B is close to the parameter value. And if you think about what we know about standard deviation, for that X bar, the green picture, you're going to have a smaller standard deviation. And so that means that you're going to have way more higher percent of your data close to your actual mu, or your mean in this case. Okay, in sum, to make an inference about a population parameter, we use the sample statistic with a sampling distribution that is unbiased and has a small standard deviation, usually smaller than the standard deviation of other unbiased sample statistics. So the deviation of this sample statistic won't concern us really, and we won't worry about it too much, because the best statistic for estimating specific parameters is a matter of record. We'll simply present an unbiased estimator with its standard deviation for each population parameter that we consider. So we're going to just specify this is our standard error of our statistic. We know what it is, it's this big, and that's our standard deviation. So we just use that and we say this is our error. Okay, so I want to list out for us 2 criteria for choosing an estimator. And so to choose our point estimator, the first thing we want to look for is an unbiased sampling distribution. And the second thing, the tiebreaker, remember, is we want the smaller standard deviation. All right, let's take a look at an example where we're going to calculate all these measures ourselves. Okay, consider the following probability distribution. So we have x and we have p of x, and we can see that we have 3 possibilities for x, 2, 4, and 9. And then when we look at the probability of each of them, we see that they're all 1/3. So they're equally probable, these 3 items. Okay, and we want to calculate our mu for this distribution. Remember, to find mu when we have a list with each of its probabilities is we just multiply them, x times the p of x, and then we just add them up, and that gives us our mu. So let's do that, and I'm just going to use fraction multiplication because dividing by 3, I know I'm going to have repeating decimals, so I'm just going to write it as fraction form. So 2/3, 4/3, and 9/3, and I know 9/3 reduces to 3, so if I was going to enter this into my math lab, I would write the 3 instead of 9/3, but I just want to leave them as all thirds because I know I have to add them next, and it's really easy to add if they all have the same denominator. So I have 9 plus 4 is 13, 14, 15, so I end up with 15 thirds, and then at this point I definitely want to reduce to 5, and that's going to be my mu. So that's my answer for part A. So finding mu just like we have in the past. Find the sampling distribution of the sample mean x bar, so we're talking about x bar, for a sample of n equals 3 measurements from this distribution, and show that x bar is an unbiased estimator of mu. So we want to see the sampling distribution, and I'm going to read ahead because on these problems sometimes you're going to have to do a few things, and it's a little easier if you leave space in your tables for it. The next thing I'll have to do is find a sampling distribution of the sample median m for a random sample of n equals 3, so that's the same size as we had before, n equals 3 measurements from this distribution, and show that the median is a biased estimator of mu. And then we have a question: if you wanted to use the sample of 3 measurements again from this population to estimate mu, which estimator would you use? And right now I can kind of look back and I have a pretty good guess because it says show that x bar is an unbiased estimator of mu, and this one says show that the mean is a biased estimator of mu. So right there I know I'm probably going to want to end up with that x bar, but I want to go ahead and calculate first and make sure. But I think the x bar is going to be the better point estimator because it's unbiased. Okay, so let's look at a table that will help us calculate all this. And so first thing I want to have on my table is sample. So I have to write what my sample is, and then I have to find the x bar, and I'll have to find the median. Okay, so I'm going to make a big table to do this. If I can fit it all on here. Tables look much better on regular paper. Okay, my sample I have, remember, it's 2, 4, and 9, so my values are 2, 4, and 9. And my probability when n equals 3, because I'm going to do 3 in a row, so my first possibility, let's write a couple of them down, is going to be 2, 2, 2. So for, I pick, like say they're in a hat, I pick one, I put it back in, I pick one again, say I get 2 all 3 times, and then my next possibility is going to be 2, 2, 4, and then 2, 2, 9. And then say I do 2, 4, 2, 2, 4, 4, 2, 4, 9, and then 2, 9, 2, 2, 9, 4, 2, 9, 9. Okay, so that's my first set, and that's just starting my first draw as a 2, and then all the other possibilities that I could have. So we're going to have to repeat that same set another time and another time, one starting with 4 and one starting with 9. So we could write all those out. And it's going to start off, let's see if I'll be able to fit them all. So it's going to start with 4 this time. 4, 2, 2, 4, 2, 4, 4, 2, 9. And then 4, 4, 2, 4, 4, 4, 4, 4, 9. And then 4, 9, 2, 4, 9, 4, 4, 9, 9. And so now I've gotten all the ones that start with 4. Now I just need to do all the ones that start with 9. And so I'm almost there. So I'll have 9, 2, 2. So I have 9, 2, 2, 9, 2, 4, 9, 2, 9, 9, 4, 2, 9, 4, 4, 9, 4, 9. See if I have more space. I do, just barely enough. So 9, 9, 2, 9, 9, 4, 9, 9, 9. So we do want to leave a lot of space for writing these out. And then I need to find my X bar for each of them. So remember, to find X bar, it's the average of all of these. So the average of all my 2's, remember to get that, you add them all up. 2, 4, 6, divide by how many you have. 6 divided by 3, that gives me 2. And I can go through and do that for each of these. 4, 5, 6, 7, 8 divided by 2 by 3. So I'm going to leave that as a fraction, so 8 thirds. And then 9, 10, 11, 12, 13, not divisible by 3, so 13 thirds. 4, 5, 6, 7, 8, there's another 8 thirds. 4, 8, 9, 10, so there's 10 thirds. 9 plus 4 is 13, 14, 15, so that's going to be 5. 9, 11, 13, so 13 thirds. And then 9, 13, 14, 15, so that's going to be 5 again. And then 18, 19, 20, so we have 20 thirds. And then 4, 5, 6, 7, 8, so 8 thirds. And we go on like this, so 10 thirds, until we have all of them listed. So 13, 14, 15, so that's going to be 5, 8, 9, 10 thirds. And then this one's going to be a 4, I can tell because they're all 4s. 13, 14, 15, 16, 17 thirds. And then 9, 10, 11, 12, 13, 14, 15, so 5. And then 13, 14, 15, 16, 17 thirds. And then 18, 19, 20, 22 thirds. And then 9, 10, 11, 12, 13 thirds. And 9, 13, 15 thirds, so there's another 5. And then 18, 19, 20 thirds. 9 and 4 is 13, 14, 15, so another 5. 9, 13, 15, 17. And 18, 20, 22. 18, 20. And 18, 20, 22. And that one, obviously, a 9. Okay, so I got all their averages, their means, and now I need the median. So I have the 3 numbers listed, but what I need to do is, in my head, put them in order and pick the middle number. So for the first one, the 2's are all in order, so I just take the middle one and it's just a 2. And then these are in order, so it's a 2 again. These are in order, 2. These are not in order, but if I order them in my head, it'll be 2, 2, 4, so my middle number is a 2 again. This one's in order, so 4. This one's in order, so 4. This one's not in order, it'll be a 2. That one will be a 4. And this one's in order, so it's a 9. This one's not in order, but it's reverse order, so I can see it's a 2. Switch the first 2, and I can see that my median's a 4. That one's a 4. That one's a 4. Reverse order, that one's a 4. That one's a 4. That one is a 4. And another 4. Finally, we have a 9 to change things up just a little bit. And then on these last few, I have a 2, a 4, a 9, a 4, a 4. That one's going to be a 9. That one will be a 9, a 9, and a 9. So there's all my medians. Now, I did two things at once, which was I knew I was going to need the means and the medians, so I did them all in the table at the same time, but really what I wanted bad was for the first part, for part B, was just the x bars. So what I want to do now is look at the probability of each one of these x bars. So I'm looking at the probability of each x bar. And it looks like it's going to be the same probability for each mean because I have the same number. But I want to know if they're independent events, like the outcome of one does not affect the other, and because we were replacing back into the bag and we could pull out another 2, for example, then we know that we can just multiply the probabilities. So I'll have the probability for the first draw, the probability for the second draw, probability for the third draw. Now we knew each probability was 1/3, and that's from that table that's at the top of the page. So when I multiply all those together, I get 1/27. And if you actually count all of these items, 2, 2, 2, that was 1 up above there, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I have 3 sets of 9, so that's where the 27 could come from as well. So each of them has, because they have equal probabilities, you can do it that way. But I have 1 out of 27 for each one of those probabilities. So that's important to know. So what I want to do now is make a table. Yeah, so what I want to do now is make a table of the x bars that I came up with. So I have x bar, and then I need to write the probability of x bar, and then x bar times the probability of x bar. So I'm going to make just a small table for here. It won't take nearly as long, I promise. Okay. And so what I'm doing is looking at all my x bars. The first one I see is a 2. And then I'm coming down. The next thing is an 8/3, and I think that's the smallest one after the 2. So 8/3 is next. And then I see a 10/3, so I'm going to put that. And then a 13/3. And then the 5, which is 15/3. And then I have a 20/3, but I also have a 17, so let's put that 17/3 next, and then the 20/3. And then let's go down a little bit, 20/3, there's a 22, and then 9. So I don't have very many more, but 22/3 and 9. And 1, 2, 3, 4, 5. Oh. And I did have a 4, so I do need to slide things down and fit that 4 in. And there goes the 4. Okay, so then what I want to do next is look at my probability of each of those. And so to do that, I have to know how many times it appeared on my chart over here. So the 2 only happened 1 time. So it has the probability of 1 time there. So it's going to be 2 times, or just a single 1/27th. And then for my calculating the mean here, it's going to be 2 times 1/27 or 2/27. I'm just going to leave it as a fraction like this. And then I have 8/3, so I have I already counted the 2's, so I have 1 8/3, 2, 3, and that's it. So I have 3 of those. So the probability for 8/3 is 3 over 27. And then when I multiply these two together, my 3's are going to cancel, and so I'll have 8/27. And then I want to look at 10/3. So I have 1, 2, 3, and that's it. So 3/27 again. And then when I multiply these two again, the 3's cancel, and so I have 10/27. And then I want to look at 13/3. So I have 1, 2, 3, so I have 3 of those, so it'll be 3/27, and multiply them again, and I get 13/27. Then 4, I'm looking, I only have a single 4, so that's going to be a 1/27, and then when I multiply, it'll be 4. 4/27. And then I look at the 5, so I have 1, 2, 3, 4, 5, 6 of them, so I have 6/27. And when I multiply here, I'm going to get 30/27. And then 17/3, there's a 20, there's 1, 2, 3. I don't think I have any more of those. So 3/27 again. And then when I multiply those, I'll get the 17/27. And then 20/3, there's 1, 2, 3. So I have 3 of them. And multiplying here, so I'll get 20/27. And then 22/3. 1, 2, 3 of them. So again, 3/27. And when I multiply, I get 22/27. And then the last one, 9, I have just one time, 1/27. And when I multiply those, I get 9/27. Now, if I'm just trying to find the probability of each of those, that would be this middle column here. And remember, probabilities should add up to one whole. So let's check that out. So I have, there's a 4, plus that 6 is 10, and plus another 6 is 16. And that'll be 20, 23, 24, 25, 26, 27. So there I have 27/27, and that checks out. That does equal 1. That's good. And then what I'm doing here is finding the mean of my distribution for all my samples of size 3 of where their x-bars are. So these are all the x-bars that I came up with, the probability that each of them was going to occur based on this sample that I have. And then so I'm adding all of those up to see what is the mean for that distribution of the possible x-bars for this problem. So I want to add up all of these numbers, and because I have the same denominator, that's handy, so I can just do divided by 27 like that, and then add up all those numerators. So I can see that first pair gives me a 10, and then I have another 10, and then I have a 13, I have a 34, just add them all however you like, and then that's a 37 and a 31, and so I get 135, and let's divide that by 27, and that does equal 5. So what we found is that our mean for our X-bar distribution is a 5. And now if I look back, that was the mean based on the actual probabilities that we got for this, and its mean was also 5. And remember, when the mean for the actual population and the mean for the sampling distribution that you're looking at match, then you have an unbiased estimator. So I can say that my mean for my X-bar sampling distribution equals 5, which equals mu for population. So the mean for X-bar is unbiased. And is an unbiased estimator of mu. Okay, so that's very nice. Now I just have one more thing that I need to do here, and that is for part, well, a couple, but what I did on part B there is I showed that X-bar is an unbiased estimator of mu. And the way I did that was I listed out all of the sample points, because they told me n equals 3, so I listed out all of the sample points. I found the mean for every sample point, and then I looked at all those possible means, and I listed out all the possible means, wrote down their probability. Remember, I found the probability by analyzing the situation. I have 3 equally likely possibilities for every draw, and so I just multiplied them all together and got 1/27. And then I used that 1/27th as the probability based on how many times 2 appeared. It was 1/27. 8/3 appeared 3 times, so it was 3 times 1/27 or 3/27. And then calculated that whole table for all the probabilities, and then I just multiplied my X-bar times the probability of X-bar. Oops, that should have an X-bar on it. Let me fix that. Times the probability of X-bar, and then that's where I got this column. And remember, that's how you find the mean for a distribution. And so when I added all those up and divided by the 27, that was the common denominator, I came up with 5. So the mean for my X-bars is 5. And because that mean for the X-bar sampling distribution was the same as the population mean, it's an unbiased estimator of the population mean. Okay, now I need to do that same thing. I'm going to shrink this. I know you might need to use a separate piece of paper, so I apologize there, but I'm going to shrink this down a little bit so that I have room to do an analysis for my median, because I need to do the same thing for the median. So move this up, and I think that will give me enough space to do the median. So let's check for the median. What do we have to do? We already calculated all the medians, and it's going to be a lot quicker because you can see that my medians and the probability of my medians, and then the median times the probability of the median. Those are the 3 columns I need, but I only have 3 rows, which makes it very quick. So I just have a 2 for a median, I have a 4 showing up, and I have a 9 showing up. And that makes sense because we're not doing an average, we're just picking the middle number. So we're only going to have all of the items in our population as our possible medians. So then when I look at 2, I'm just counting. I have 1, 2, 3, 4, 5, 6. Let's see if we have any more down below there. Just 6 of those. So it's 6, and I still have the same probability for each row on that table because there are 27 items on that table, so I have 6 out of 27 for this one. When I multiply, it gives me 12 out of 27, so I'm just going to leave it as a fraction, even though I know it with 27 as the denominator. Even though I know it can reduce, I'll reduce at the end. And remember, when you're working in MyMathLab, if you have to enter probabilities, you will need to reduce them. So even though on the table I'm leaving them unreduced, if you have them in MyMathLab, you'll have to reduce. So the 4, I missed one, it looks like. Let me check. 1, 2, 3, 4, 5, 6. I did miss one. So there's a 7th right there. That changes things slightly. Fix that up. So 7 out of 27, and then when I multiply, 14 out of 27. And then looking at the 4s, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 of the 4s. So 13 out of 27. And when I multiply that, it's going to be 4 times 13, or 52 out of 27. And then let's look at the 9s. I have 1, 2, 3, 4. 5, 6, 7 of those. 7 out of 27. And when I multiply those, 9 times 7 is 63 27ths. Now remember, we can double check that I didn't miss anything. And when I add those up, 13 and 7 is 20. And then 7 more, that gives me 27. So that does add up to a whole 1. Which it should for probabilities, so I know I got them all. And then when I add these up to find the mean, it'll be 63 plus 52 plus 14, which is 129 over 27. And I'll divide by 27. And I get I'll show it properly. The mean of the medians equals 4.78. Okay, so since this mean of our medians is not equal to our sample mean, where we got the 5 there, this median is an unbiased predictor. So I'll write that. I think I have space below. So the mean of the median sampling equals 4.78, which is not equal to mu, for the population, so the mean of the medians is a biased estimator. So this could be the answer for part B, the answer for part C, and then the answer for part D. Let's go back and take a look at that one again. And that D says, if you wanted to use a sample of 3 measurements, which we just calculated for, from this population to estimate mu, which estimator would you use and why? And so because the mean of the X bars is unbiased, I would use as a point estimator for the mean, or for mu. Okay, so just recapping, because this is our only example for this lesson, if we were looking at some other measure, for example, the standard deviation of x bar, instead of putting the x bar here, we would maybe find the x bar first and then find the standard deviation. Remember, you can do this for any measure for a population. You list out all of the possibilities and then calculate whatever that measure is. So we calculated x bar and we calculated the median. We could also calculate the standard deviation. And if you wanted to do the standard deviation, remember it's based on this little sample right here. So you would do, remember we do the, I'll just show you real quick. So if you have your x's 2, 2, 2 for that first sample, and then remember you want to look at your x squared, so you're going to have 4, 4, 4, and then remember we do that little table. See if I can move this. Okay, so I just moved that down a little bit. So find the x bars and you square them, add up the squared, so that's going to be 4, 8, 12, so I'll have 12, and then add up your 2, so 2, 4, 6, and then square that, and so you have 36, and then that little formula, remember, is going to be the 12 minus 36 over 1, 2, 3 divided by 2, and then take that square root of everything. The other formula might be a little bit quicker because we have such small samples, but you could use either formula, remember, to find if you needed to find the standard deviation. So that's for your standard deviation for your sample. So you may want to do that. You also, if you had to find the variance for an x bar sample, you would just not take the square root, and then you do the same thing as you're doing here. You're going to list out all of your standard deviations and make a second list that summarizes them like we did here, like all the possible standard deviations for this set of data. Find the probability based on how many times they occurred in the list, and then multiply the two, and then you would get your bottom number here, which would be your estimate for your standard deviation for the population. Okay, so we're going to use the same formulas that we've used before for standard deviation and variance. It'll just be in a new context.